the pictures. If you have a very low frequency, you have bigger droplets, and you end up with globular metal transfer, so we are talking about short circuit. If you have a too high frequency, perhaps you don't have enough time to transfer the small droplet at the wire tip, and the wire and the transfer became a little bit crazy. So when you have a suitable frequency, short circuit works as it's supposed to do. That criterion that we call the IVCC is just a name, just an acronym. As you vary the voltage within the short circuit range, for lower voltage you cannot have energy enough for the arc, so you don't have let's say a good stability. So you have a high index, and when you get a good voltage setup, the index decreases, reaching a minimum, and after that it starts increasing. So here, let's say we have a better, the best or most suitable adjustment this voltage for short circuit. That's hopefully what that index says. And when you go for higher voltage, it starts decreasing again because of globular metal transfer. That's why frequency is important. To say, okay, you stop here, that's your best point for welding with short circuit. I'll just present the tables. It is in that paper. If you have any doubts or everything is tabulated, everything is the table, I'll just skip that if you allow me. For Austenitic and Duplex, okay, our two wire feed speed, the gases, voltage, the current, everything that we have. Right here we are just analyzing the position efficiency, which was pretty good, 99%, 99, 98, 97% is definitely a good number for short circuit and the position efficiency. And also we look for the index IVCC, which means the lower the better. Let's see, just the table, we are not analyzing the table, just if you get interested, please, we have that in the paper. Okay, let's go through the graphs, much more important. Okay, spattering in our case was really low, 2.10% maximum, so you have an efficiency of, let's say, 97.9, it's pretty good. So just 2% of material flying away from the weld pool. So the position efficiency above 96%. The difference here could be fumes, small, let's say, silicates that stay aside of the weld bead, things like that. But let's say the pictures. Okay, the spattering mass. For the Austenitic, I must say that the behavior that we could expect did not happen all the time, because we expected to see a minimum of the index, which happened in this case. For this particular situation, 2.8 meters per minute and 2% of CO2. But not always the same, they follow, because what we expected that we would have a minimum of the IVCC and a maximum of the position efficiency, so the curve would be upward here, and a minimum of spattering mass. But because Austenitic, definitely the range that we select, let's say, was a good range for all the voltage that we select. So we cannot see a clear range here, because we expect a small valley for the IVCC. Let's say that's the best voltage, would be the best deposition, and that would be the smallest spattering index, but spattering mass, sorry. But we didn't see that. We see, if we make a statistical analysis, this is more or less constant here. So, okay, for stainless steel, the index didn't show, let's say, the best of itself, but we still have some points we see really low value of the index, and let's say the position efficiency keep more or less the same. So, but it is a little bit tricky for Austenitic. But for the Duplex, no, we can see okay, above 20 volts, we cannot analyze because it's they have the cutting frequency. So, but from 14 to 20 volts, we clearly see the valley here, the small values. That small values lead us to the smallest spattering mass and the highest deposition efficiency. Let's say for duplex steel, stainless steel, the index works. What I mean by work? It has a small value for the index because it means the smallest deviation of open arc and short circuit times, and we reach the highest deposition efficiency and the smallest spattering mass. So for duplex it worked pretty well, and let's say if you select a good voltage would be 16 volts. If we take a statistical analysis, we see that the higher the wire feed speed, we have a small trend, not for the both wires, but let's say a trend to reduce the deposition efficiency. For the shielding gas, is not that clear. So because we mixed all the variables are connected, wire feed speed, voltage setup. It became a little bit tricky to analyze by a statistical way. So, but we see roughly, if you can try to abstract or to take some numbers from here, the regularity index would be smaller for 2.8 meters per minute and argon plus 2% CO2, which hopefully lead to a better deposition efficiency. If you look here, okay, it's not properly statistical, you cannot say that, all right. But we see a trend for higher deposition efficiency for for the smaller wire feed speed, and for argon plus 2% CO2, which is something that we expect, that 2% CO2 would be better than 2% O2 for short circuit metal transfer. We make an analysis of how far the spattering goes. You can select your condition by, let's say, okay, I would like that voltage setup, that shielding gas to read, let's say, a smaller spattering, but closer to the weld bead, or very thin spattering away from the bead. Depends if you are in automotive index, you prefer very thin spatter very away from the weld bead, so you don't have much problem to remove that. If you have a heavy industry, perhaps it's better to have a bigger spattering close to weld bead, so when you try to grind off, you remove the spattering. Well, it depends on the situation. But here, we can say the spattering is concentrated beyond 800 millimeters away from the bead, so it's good. If you need to paint, I know stainless steel is hard to paint, but if you want some static presentation of your build, as voltage is increased, the amount of spattering close to the weld bead is increased because the droplet gets bigger, so spattering gets bigger. The lower the spattering, the farther it reaches. So it's of course it's a bit obvious. But here, you know, all the curves I'll leave for you if someone wants to analyze for a small close range or high range, small spatter, big spatter. So let's go for the conclusion. The material loss to spattering was low and the position was pretty good, 96% of deposition efficiency, which means that only 4% of the material we lost. For duplex stainless steel wire, the lower regularity index value, the higher the deposition was. So that means that, okay, you can use this index to search for better welding parameters for duplex stainless steel. On the other hand, for stainless steel, we cannot. Perhaps, I don't know, we still have to look into the metallurgy, definitely is important, because this index works really well for carbon steel, which means there's a lot of ferritic. So maybe the 50% of ferritic part in the duplex could make it work like a carbon steel, we don't know. We still have to look for the metallurgy. But for austenitic, we saw that there's a really flat curve for spattering, for the index, which means that, okay, anywhere in between 14 and 20 volts that you select, you end up with a good weld bed and low spattering. So perhaps we can look for more geometrical features of the wire. Wire feed speed and shielding gas present a very small influence on sputtering generation. We saw that the smaller the wire feed, the lower the sputtering, and for argon plus 2% CO2, we got better results. But statistically, you cannot say that, it's just a trend. Regularity index decreases as wire feed speed increases, and regularity is higher for, as I said, argon 2% CO2. Finally, I would like to thank Sandvik and Aperan, which is ArcelorMittal company, for providing us the wire, the filler wire and the base metal, and the Brazilian agencies that granted our research, and thank you all for being presented. Thank you very much.